Welcome back, Shubho Navabarsha to all my viewers.
Tomorrow was opening day of Bengali New Year.
In my previous video, I had discussed about ring theory. Today I will discuss the new topic, field theory. Firstly, I will discuss ring theory again, but at first I will discuss the field theory because I will discuss in my next video vector space and metric space. And to understand vector space and metric space elaborately, we have to at first understand field theory. In abstract algebra, there is 4 operations: addition, subtraction, multiplication and division. In abstract algebra, subtraction means addition with negative number. In abstract algebra, 7 minus 2 means 7 plus minus, here the operation actually the plus minus 2. Here the addition and subtraction actually the addition and addition inverses. There exists more than one kind of inverse. Let's see. In abstract algebra, 3 divided by 5 means 3 times 1 over 5. Here the operation is multiplication and division. Here this means actually the multiplication and multiplicative inverse. Okay? Field actually is a set F together with 2 operations addition and multiplication which has following properties. 1. F has a commutative ring under addition and multiplication. Second, every non-zero element F belongs to F has a multiplicative inverse. Consider G belongs to F, then F composition G equal to G composition F equal to 1. Actually F is a field, means if it is a ring such that F minus singleton 0 is a group under multiplication. Consider the set of rational numbers. Obviously they are commutative with addition. Also they are commutative with multiplication. And all element has multiplicative inverse. So set of rational number is a field. Okay? Well, but if you consider Z, then obviously Z is a group under addition. Here Z is abelian group. But here in Z has no multiplicative inverse. Because if you consider the element 2, then the multiplicative inverse of 2 would be 1 over 2, but 1 over 2 not belongs to Z. Similarly, if you consider 3, then multiplicative inverse of 3 would be 1 over 3, which also not belongs to integer. That means here any element has no multiplicative inverse. So the integer is not a field. Similarly, real number, complex number and Z mod Pz. When P is a prime number, otherwise not field. Let's check oneself. When P is a composite number, then this is not field. Because when this is the composite number, then every element does not have multiplicative inverse. And if we consider F equal to Z mod Pz, this is actually the finite field. Here only finitely many elements contains. Q, R, C, these are not finite field. These are contain infinitely many elements. So these are infinite field. And Q, R, these are subfield of set of complex number. Definition of subfield is, let K be a field. A subfield, here the main field is denoted as K and subfield is denoted as capital F of the field K is a subfield which is satisfying two operations. F is a subgroup of additive group K under addition, and F minus singleton set 0 is a subgroup of the multiplicative group of K minus singleton set 0 under multiplication. Now I will see one nice concept, field extension. And this is not only important for field theory, this is important for also vector space. The definition is, if F is a subfield of the field K, then we can say K is a field extension of the field F. The notation is K divided by F. That means when I will write K divided by F, that implies K is an extension field and F is subfield. If we want to draw the picture, here F is the smaller algebraic structure and K means whole ring is the larger algebraic structure. Actually, a field extension of a field is a monomorphism which is defined as L from F to K, where F is a base or small field and K is a large or extension field. And the mapping is such type. Here the mapping F to K. Here K is extension field and F is a small field. Are you getting the idea? This is actually the monomorphism. Now I will see some example of extension field. At first I will say what is the smallest extension field of Q that contains square root of 2. At first just think. See, the field must contains all sum, differences and quotient of numbers. And these would be minus square root of 2, 1 over square root of 2, 6 plus square root of 2, square root of 2 plus 3 over 3 over 2 whole cube, so on. Okay. As for example, if we consider square root of 2 plus 3 over 2 whole cube, then this would be this, just this type, and this would be 19 over 80 plus 25 over 4 times square root of 2. In fact, all this number actually written as b square root of 2, where AB belongs to Q. Have you understood? How like the element of extension field Q square root of 2? Well, that means the smallest extension of Q that contains square root of 2 is called Q adjoint square root of 2. And the element of Q square root of 2 is set of those element A plus B square root of 2, where AB belongs to Q. So extended Q as Q to the power 1/3 Qi, where I is square root of minus 1. That means there exists infinite number of extension field of rational number. Now I will see new type of extension of rational number. Let alpha be solution of the polynomial equation, where the coefficient of the polynomial are fraction. Then alpha is a root of this solution, but alpha not belongs to rational number. So Q alpha is an extension field of Q. And this type of extension is called algebraic extension. Just recall the fundamental theorem of algebra. If a polynomial of rational coefficient does not have root in rational number, But we all of us know by fundamental theorem algebra, if a polynomial of rational coefficient does not have root of rational number, but it must obviously root in complex number. So, complex number is extension field of rational number. Now I will say new type of extension field. We all of us know convergent sequence. Consider a sequence which belongs to Q, and this sequence converges to the number L, where L does not belongs to Q. We all of us know R is a complete space, so obviously this sequence converts to real number. So this is the extension field of rational number. My question, okay. What is the extension of real number? If we consider Ri, then obviously this is the complex number. So obviously this is the extension of real number. Few minutes ago, I had seen the expression algebraic extension. Now I will see what is the actual definition of algebraic extension. Algebraic extension. What is the definition of algebraic extension actually? The definition is K over F be a field extension where F is a subfield of the field K. Let alpha belongs to K. Then we can say alpha is algebraic over F if there exists a polynomial fx in fx such that f alpha equal to 0. Means if alpha is a root of any polynomial equation, then we can say alpha is algebraic number, and this extension is called algebraic extension. Example, R divided by Q. Here square root of 2 is algebraic over rational number because square root of 2 is root of the equation x square minus 2 which belongs to Qx. Similarly, if we consider 2 to the power 1/5, this is actually algebraic over rational number because this is the root of the polynomial x to the power 5 minus 2. Similarly, C divided by Q, here I belongs to C is algebraic over 2 because this is the root of the polynomial x square plus 1. But if we consider R divided by Q, then the point pi and E are not algebraic over rational number. So, this is called transcendental over rational number because there exists no polynomial which has root pi and E. When I will consider the field Q, that means when I will consider those polynomial whose coefficient be rational number. Are you getting? That means definition of transcendental polynomial is alpha is the transcendental over the field A if it is not algebraic. Obviously pi and E are algebraic over real number. Thus, pi and E are root of the polynomial x minus pi, x minus E, and those polynomial belongs to Rx. So, algebraic and transcendental are properties of field because equation x minus pi are transcendental equation over the field Q, but in Rx, x minus pi is an algebraic equation over the field R. So, when there exists a extension field K, then obviously there exists a base field F and all part depends on this base field. Are you getting how field theory is more important? This part all depends on field, not the points of the. And last question. Can we extend complex number with new numbers? Just think. Limit of convergence sequence of complex number always lie in complex number. Also, just recall, solution of polynomial equation always lie in complex number because complex number is algebraically closed. So, we cannot extend complex number with new numbers. Are you getting? Well, extension of complex number means C with just one variable x. That means set a polynomial of rational number whose coefficient be complex number. And obviously Cx is a field. We can add more variables Cx, y, so on. Okay, today I will stop here. In my next video, I will discuss vector space. But at first, I will highly recommend you. Please pay attention in today's video because the field is more important for higher study. Vector space, metric space, all depends on field theory. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos.